ratio of the coefficients to determine the limit. So this limit is 1. So to guarantee convergence, that has to be less than 1. So I'm going to draw myself a little arrow to save some space. So that means, simplifying this, we're solving this inequality, remove the negative signs, or the absolute value signs, and now to get x by itself, we multiply through by 4. So here's my IOC for now, but now we know the endpoints that we have to test. Okay, so I'm going to draw a little line around this, slide my paper up. So let's, I guess, do the x equals 4, test endpoint at x equals 4. So recall that means take 4, plug it in for x in the original series. N equals 1 to infinity, n. So instead of x to the n, it becomes 4 to the n all over, 4 to the n, n squared plus 1. So something nice happens. This cancels. And this equals n equals 1 to infinity, n over n squared plus 1. So at this point, I'm going to pick a test. I can either run DCT, LCT, or go from there. So I'm going to do LCT. I'm going to pick LCT, take a look at the numerator and denominator. Going to let b sub n equal 1 over n. So now I'm going to take the limit of a sub n over b sub n as n goes to infinity. So I get n over n squared plus 1 all over 1 over n. And this becomes, flip the guy, n squared over n squared plus 1. The powers are the same. I can take the ratio of the coefficients. So this is 1. This is our C. And if you remember from LCT, as long as that number is between 0 and infinity, I either both converge or both diverge. So since b sub n is a known divergent series, then a sub n is divergent as well. So there we do not include that endpoint. It's not included. Okay, so continuing on with our analysis, we're going to test the other endpoint. So this time we're going to test endpoint x equals negative 4. So n equals 1 to infinity, n, this becomes negative 4 to the n, all over 4 to the n, n squared plus 1. Now we have a negative. We're going to rewrite it to isolate the term that affects the alternating. So minus 1 to the n, 4 to the n, all over 4 to the n, n squared plus 1. So just like we saw in the other endpoint problem, those cancel. So n equals 1 to infinity, minus 1 to the n. I lost an n. There it is. N over n squared plus 1. So since it's an alternating series, I have to run Leibniz's theorem. So 1, 2, 3. And from what we've learned, u sub n is n over n squared plus 1. All right. So, first thing, u sub n is positive everywhere, so we get a check. Is u sub n plus 1 less than or equal to u sub n? Well, the terms will decrease as n grows, so we get a check for that as well. Then the limit as n goes to infinity of u sub n is going to be equal to 0. So by Leibniz, we converge. Now we have to check for a conflict. Now, this one isn't a simple p-series. We're going to have to run another test. So we're going to do the same thing we did with the last one. And so this is going to look super familiar. So we're going to run LCT. We're comparing the ratio. So we can use what we did over here as a guideline. You don't even need to rerun it if you don't want to, but it's going to be the same b sub n. So you're going to get the same answer as you got for the other one. So if you want to not write this out, save time, you could just say from evaluating x equal 4, this diverges. But I'll go ahead and write it out. So remember that either both converge or both diverge, and since we know b sub n is divergent, we can say since b sub n diverges, then u sub n diverges as well. Now, therefore, we have a conflict. Our analysis from Leibniz said that we converged. Our analysis from looking just at u sub n said we diverged. So when we have a conflict, that means we are conditionally convergent at that endpoint. So we are conditionally convergent at x equals -4. So now we have to summarize. So our interval of convergence goes from -4 to 4. We converge absolutely from -4 to 4, and then we converge conditionally at the point x equals -4. I'm going to stop this video. Oh, actually, I'm going to keep going. Okay, we'll do the last example. The very last example of calculus, and we can't see the problem, so we have to fix this. So this should look like -2 to the n. And this says n plus 1, and then we have x minus 1 to the n power, n equals 0 to infinity. Alright, so same. This time we're going to have an alternating series, so this is slightly different than the other ones, but we're going to use the ratio test again. Okay, a to the n plus 1 over a to the n. We're going to take the limit. Okay, so this becomes -2 to the n plus 1. And then we have n plus 1 plus 1, x minus 1 to the n plus 1.